Hello, my name is Mason Cipollini with my partners Mackenna and Mayra Mendoza. This is the Schlieren lab for OPTI 471A.
The STAR test is a simple way to evaluate lens quality by looking at how a point source forms an image when we move slightly inside and outside the focus. It helps us see aberrations like coma, astigmatism, and spherical aberrations without needing an interferometer. For the procedures, we used a helium neon laser, a spatial filter, and an achromatic doublet as a test lens. We formed the STAR image with a microscope objective and observed how the pattern changed as we moved the focus. We also intentionally misaligned the lens to induce coma so we could see how the pattern became asymmetric. Our results matched what we expected. Inside focus, we saw a bright center with ring, and outside focus, the pattern flipped, just like theory predicts. When we rotated or shifted the lens, coma appeared as a comet-shaped pattern with a tail that changed direction depending on focus. These results clearly showed the typical signature of a lens aberration.
Now I'll go over the Foucault test portion of the lab. The goal of this test is to use a knife edge placed at the focal plane of the lens to turn tiny wavefront errors into brightness and shadow patterns that we can see. After aligning the spatially filtered Heaney onto the lens, we removed the microscope objective and put a razor blade on a microscope stage at the focus. By translating the blade across the beam and then moving it slightly inside and outside of focus, we watched how different zones of the pupil darkened at different times. In our recorded image, you can see the shadow pattern changing between paraxial, mid, and marginal focus, which is what we expect for a lens with small amount of spherical aberration but overall decent optical quality.
Schlieren imaging is an optical technique that allows us to visualize refractive index changes in air as the emissions of certain physical effects bend light differently. They create refractive index gradients, which through ray deflection in Schlieren imaging, we can turn those gradients into a visual picture. This is important as some of these effects that would be otherwise invisible to us, such as temperature plumes, gas flow, and turbulence, are key in identifying emission hazards or ultra-high velocity measurements. Our procedure involves shining a point source at a curved mirror where the light is reflected and refocused at a knife edge. A camera is then placed directly behind the blade, which collects and sends the Schlieren image to the proper software. What resulted from this was a visualization of the flow of air at different temperatures. We could clearly see how hot air would rise and cold air would sink. This result certainly met our expectations and provided some neat footage.
Overall, we like that both the STAR and Foucault tests gave really intuitive visual feedback about aberrations, but they were also very alignment sensitive. And small errors in focus or centering changed the patterns a lot, so getting good data took patience and careful adjustment. And we also enjoyed the fact that the Schlieren imaging, we were able to be very creative with the photos.